Hello everyone. Today let's solve the problem small operations, right? So here this was asked in Codeforces around 1027 division 3, right? So what the question states here, I insist you to go through the question. I insist you to go through the question and understand the question. So I'll just summarize the question so that it will be easier for us to solve the problem, right? So what the question states here, we are given the integers x, y, and k. So in the input we have 3. You can just check the input basically. First, for the first input we have 4, 6 and 3, right? So this is nothing but 4 is nothing but x and 6 is nothing but y, and this one x, y and k, sorry, not z. So k is nothing but the 3 here. We are given integers x, y and k. So in one move we have to choose one less than or equal to a, less than or equal to k. In one move, in only one move, we need to check this one less than or equal to a, less than or equal to k, and set x equals x into a. This part is very important, right? So and the set x equals x into a, x equals x into a, or x equals x power a as well, or x equals x power a, right? So in one move we have to choose one less than or equal to a, less than or equal to k, this one, and set x equals, we can set x equals x into a or x to the power of a. We can set x equals x into a or x to the power of a, meaning x to the power of a, right? So what is our main goal, right? So we have to reach this part. We have to reach x equals y. We have to reach x equals y in the minimum number of operations. So our main goal is to reach x equals y, right? So what are the operations? Basically we have to choose one less than or equal to a, less than or equal to k. This is fine. So x means and we can set either x equals x into a or x equals x to the power of a. These two operations we can do, right? So our main goal is to reach x equals y. Our main goal is to reach x equals y in the minimum number of operations. In the minimum number of operations, our main goal is to reach x equals y in the minimum number of operations, or we can return minus 1, or we can return minus 1 if impossible, or we can return minus 1 if this one, if impossible. We have to do this for the t-test cases, right? So we have to do this for t-test cases. So again we have to do this for the t-test cases. What's the question again? We are given integers x, y and k. We are given integers x, y and k. In one step we have to choose one less than or equal to a, less than or equal to k, and set x equals x into a or x equals x to the power of a, right? So meaning x to the power of a. So here what is our main goal? We have to reach x equals y, this part we have to reach x equals y in the minimum number of operations, or we have to return minus 1 if impossible. Also keep this in mind. So this edge case we have to return minus 1 if impossible, right? So we have to do this for the t test cases. Means t test cases means number of test cases that they have given. We have to keep in the mind for the t test cases, right? So I hope this part is completely clear. So here let's come to the input part. We have 8 inputs. So if I hover over here, just give me a second here. If I hover over here, you can clearly see first input, second input, third, fourth, fifth, sixth, seventh, eighth, right? For the first input 4, 6, 3 we have. This is nothing but 4 is nothing but x. This one 6 is nothing but y, and 3 is nothing but the k. So here 4, 6, 3, what is the this thing? Either we can consider x equals x into a, or x equals x to the power of a. So we have, main is we have to reach x equals y, means 4 equals 6, right? Main is we have to reach x equals y, right? So that is our main goal in the minimum number of operations. In the minimum number of operations that they have given is k here, 3 operations. Minimum number of operations that we can perform is 3, nothing but k. So 4 is nothing but x, 6 is nothing but y, k is nothing but 3, or the minimum number of operations. Our goal is to reach this one, x equals y in the minimum number of operations, or return minus 1 if it is impossible. If it is impossible, within 3 we have to do. So basically here 463, let's consider the input 463, the output has to be 2. The output has to be 2 here, right? So for the 453 we cannot reach, so the output is minus 1. Same goes with 462 as well. We cannot x cannot be reached to y, so this one here in this case we have to return -1. For the fourth input we get 3, for the fifth input we get 3, for the sixth input also we get 3, and for the seventh input, this is the large input, right? So something 9,82,800 we have been given for y. So we have been given 6, and for the last input we cannot reach, so we have to return -1. I hope the question part is completely clear. I hope the question part is completely clear. What we need to do here, basically, so we need to reach x equals y in the minimum number of operations. So that's what we need to keep in mind. And we need to return -1 if it is impossible, right? So if it is impossible, we need to return -1. So I hope the question part is completely clear. Let's consider this example for the approach. First one, it will be easier. We have to get the output 2, right? 463 x, y, k, they have given 463, and we have to get the output 1, output 2. So if we understand this one, you will understand this for all basically. Let's consider step by step how can we do that, right? If we understand the first input, you'll understand for everything, I assure it basically, right? So I hope the question part is completely clear. Along with they have given beautiful examples for us to understand the question, right? I hope that part is completely clear. What shall we do now? Initially, let's discuss the approach followed by the edge cases. Initially, let's discuss the approach followed by the followed by the complexities, and then let's write the code. Initially, let's discuss the approach first. So here let's consider the same first example, or the first input they have given in the list of inputs, right? So here the first input is 463. We have already discussed this one. This is nothing but the x, this is nothing but the y, and this is nothing but the k. So here what we need to do, our goal is to reach x equals y within the minimum number of operations, right? So in the minimum number of operations, sorry, or we have to return -1 if it is impossible, right? So that's what we need to do. We have to reach x equals 5 in the minimum number of operations, or we have to return -1 if it is impossible, right? So here I hope this is clear. We can reach x equals 5 in two operations. Minimum number of operations that is required is 2. Let's see whether how can we do that, right? So basically let's come to the second step, this one, step by step explanation part. X we have 4, y equals 6, and k equals 3 we have. So first what we'll do, we will observe gcd of 4 comma 6. Quite obviously gcd is the greatest common divisor of 4 and 6 is 2 here, right? So here in this case we have 2, so we will reduce a to we have 4 and 6, right? So here this one is x and this one is y. So we will consider, we have got gcd of 4 and 6 and 2, so we will reduce this one to 4 by 2 and 6 by 2, right? So this will be 2 and 3. We got 2 and 3. So minimum steps to reduce a equals to 2, a equals to 2 to 1 using the allowed divisors in 1 to k via binary search. We'll be making use of the binary search because a equals 2 and a equals 3 we got here in this case, right? So minimum steps to reduce a equals 2 to 1 using the allowed divisors in 1 to k via binary search. For the first example, it is quite easy actually. So same goes with b equals 3 to 1 as well. So a equals 2 we have here, this nothing but a equals 2 we'll consider, b equals 3 we are considering here, right? So we need to reduce a equals 2 to 1 using the allowed devices from 1 to k via binary search. So for this we'll be making use of the binary search. So I forgot to say that one thing, we will be going with the binary search, right? So we will be going with the binary search, right, for this particular problem. So we'll be making use of the binary search to solve this particular problem along with the hash map, right? So here same goes with b equals 3 to 1. So step for a plus steps for b will be quite obviously b equals 1 plus 1. So b equals 1 plus 1. So we have to reduce this one to 1, we have to reduce this one to 1 as well. Minimum steps to reduce a equals 2 to 1 using allowed divisors in 1 to k via binary search we are doing, right? So here in this case steps we got this one 1, and for this one also we got 1. So when we sum up to this one, steps for a and steps for this one b, this will be quite obviously 1 plus 1, this will lead to 2. So the output that we got here is 2, which is equivalent to the output that they have mentioned for the first input in the within the list of inputs they have given, right, or the first example, right? So our approach works absolutely correct. In this case our approach works absolutely correct, right? So as we are completely familiar with the approach, let's discuss the complexities part very quickly. right? Let's discuss the complexities part very quickly. Here, what will be the time complexity? The time complexity would be big of log of max of x comma y into log of log y. So this one, big of log of max of x comma y into log of logarithmic y per test case. Why? Because we are making use of the binary search. Also, we will be making use of the divisor traversal, right? So divisor traversal, you will see when we write the code. So we will be going with the binary search because this one, because log of max of x comma y, log of log y because of the divisor traversal basically, right? Per test case, because log of max of x comma y into log of logarithmic y, right? Due to the binary search plus divisor traversal. And space complexity would be because of square root of y plus memo size, because of square root of y plus memo size, nothing but divisors plus memoization for previous states, right? Divisors plus memorizations per previous state, right? Divisors plus memoization per previous states, right? So big of square root of y plus memo this one memo size. So the time complexity would be big of logarithmic of max of x comma y into log of log y per test case for the code that we'll be writing in the future due to the binary search and this one divisor traversal. And the space complexity would be because of square root of y plus memo size due to the divisors plus memoization for the previous states, right? So I hope the complexities part is completely clear along with the approach. As we are completely familiar with the approach and complexities, let's start writing the code. So let's start writing the code here, right? So we'll be making use of the fast input, right? So fast input and the fast output. So let's import the input output package. So I'll just go with here import java dot input output dot star. So this is fine. And also we need the utility package. So I'll just go with java dot util dot this one star. So this is fine. So let's do one thing. Let's go with the main class. So I'll just go with public class main. So this is fine. But on this, I'll just give main here, public static void main. So this is fine. So let me delete this one. So we'll be making use of the input output exception as well. So here, let me give, or else we'll get the error. So here I'll just go with input output exception. So this is fine. So within the main class, let me do one thing. So we need the memoization map to avoid the recalculating for the sum for the same n comma k. So we can write this one later. For this, we'll be making use of the hash map basically. Again, I'm telling we'll be going with the memoization map to avoid the recalculation. So this you'll know it further. Let me write it now itself. So I'll just go with I'll forget this one. So let me write this now itself. So let me do one thing here. Let me leave the space so that it will be it looks good. So here this will be static. Let me make use of the final keyword. So we will be going with the hash map as I've said. So this will be within the map. This will be long integer. So this will be memo equals new hash map. So this is fine, I think, right? So let me do one thing. Let me come out of this one. I mean, yeah. First, within this, what shall we write first? We'll be making use of the fast input scanner and the fast output writer. Right. As usual, we'll be making use of the this one buffered reader. Instead of the buffered reader, let's do one thing. Let's make use of the fast scanner. Right. So constraints are tight here for this particular problems. Constraints are little bit tight. So let's make use of the fast input scanner instead of the buffered reader. For the output, let's make use of the print writer itself. So I'll just go with fast scanner fs equals new fast scanner. This is fine. This is nothing but the fast input scanner, and we have to go with the print writer as well. So let me go with print writer. So this one will be pw equals new print writer. So this one will be new, so buffered output stream of this will be system dot out. This is fine. Hope this is fine. So the next part is we have to read the number of test cases. For that, I'll be making use of t equals fs dot next, right? Next, let's make use of the next int here. So we have to read the number of test cases, right? Which is of the type integer basically. So let's make use of next int. So t equals fs dot next int. I hope this part is clear. So let's write the simple while loop here because we have to read all the test cases. So t minus minus greater than 0. So let's go with the current value, target value, as well as the max multiplier or the divisor, nothing but x, y, and k in our case, right? X was 4, y equals 6, and k, nothing but the max multiplier or the divisor would be k, right? So let me initialize x equals fs dot next int. This is fine. And the next part here is, so let me copy paste the same thing here. Let me copy the same thing here and paste it in the next line twice. So let me come here, paste it. I can paste it. So let me change the variable name to y. So for the final one, let me change this one to k. This is fine. Next and next, this is fine. So x, this one, line number 13, this is nothing but the current value, this is nothing but the target value. We have to reach x equals y within the minimum number of operations. K is nothing but the this one, max multiplier or the divisor. And finally, after the initialization of x, y, and k, so we have to output the result finally. For that one, let me go with the print writer pw dot println in the different lines they have asked, right? So yeah, not in the individual line. So let's go with the println. So this one will be solve of x comma y comma k. Solve is the function. So you'll will write that one later basically, right? So for now, just remember this one. So next part here is, let me come out of this one entirely. So we need to flush the output buffer. Sorry, we need to flush the output buffer. So basically, I'll just come here and give pw dot flush. This I would have written at last. Basically, we haven't written the this one. What do we call it? Solve function it as well. So this one I'm speaking of. Don't get confused here. These lines basically from 16 to 19 I would have written at last, but this is fine. I hope you understand this one, right? So let's do one thing. As we have already written this one, solve. Let's make write the solve function here, right? Let's write the solve function here. So here we need to go with the GCD, right? So we need to do one thing. Let me make use of static int solve. So the parameters I'll consider is, we have to consider is x, y, and k. We have x, y, and k as inputs. Basically, x is of the type integer, y is of the type integer, and k is of the type integer as well. So within this method or within this function, so what we'll do, if they are already equal, means if x equals y, means we were not having in the input, they have not given x equals y in any input, you can observe, right? So they have given 8 inputs in the question, right? They have not given x equals y in any input, right? So we have to consider that edge case as well. If x equals y, then we don't have to perform any operations at all, right? Our main goal is to reach the x equals y in the minimum operations within in minimum operations, right? So if the x equals y is already equals, then we have to return 0. If no transformation possible at all with k equals 1, means if x cannot be equal to y, or if k equals 1, then no transformation is possible at all with k equals 1. In that case, we have to return -1, right? Let's articulate the same thing in the form of code. Same thing. So here, if x equals y, then we have to return 0 in this case. So again, if k equals 1, then we have to return -1. So this is fine. These two edge cases, I hope this is clear. Easy ones, right? So we have to reduce x and y by GCD. So we saw the same thing in the approach. Let's articulate the same thing in the form of code here. So I'll just give here g equals GCD of x comma y. So this is fine. G equals this one, GCD of x comma y, means we are reducing x and y by GCD. So here this part, int a equals x by g, and also b equals y and y by G. So this is fine. Next part is we have to go with the steps to reduce A to 1, and also we have to go with a step to reduce B to 1. This one we have seen in the approach. So reducing the this one GCD and steps to reduce A to 1 and B to 1. That is how we get the output, final output, right? So let's do one thing. Let's articulate the same thing in the form of code here. So next step is we will be making use of the binary search to perform the steps to reduce A to 1 and step to reduce B to 1. So before writing this one, let's do one thing. I'll be going with the binary search. So we'll be making use of the binary search helper function here. So let's create the binary search function here. I'll just go with the name minimum steps binary search. So because we are going with the steps to reduce A to 1 and steps to reduce B to 1 here. So same thing, whatever we discussed in the approach, we are articulating in the form of code here. This will be min steps uh, binary search. So this is fine. So this will be int n comma int k. This is fine. So within this method, what we'll do, if it is already reduced, means if n is already 1, if we have already reduced to 1, then we have to return 0 because it is already reduced, right? So here in this case, if n equals 1, then we have to return 0. So this is the first base case, right? So let's go with the unique key for the n comma k. So I'll just go with long of not long of, basically long key which is of the type long. So this will be log mm, log of n, right? We are making use of the variable n, so this is fine, of n. And let's go with the left shift operator here, left shift operator 20 or k, right? So we are just going with the unique key for n comma k here, right? And also we have to go with the cached result as well, right? We have to go with the cached result. So here, if you remember in the line number 6, I said I'll be writing this one earlier itself. Later, don't get confused. This is nothing but the memoization map to avoid the recalculation for the same n comma k. If we have the same n and k, so we have to avoid the recalculation. For that part, we are using the memoization or the cache. Means we have to get the cache results here in the line number, for the line number 34 here, for the line number 34. So how can I write that one in the form of code? This one will be if memo dot contains key, contains key of, let's pass the key here. This is fine. Then we need to return memo dot get of key. This is fine. Memo dot get of key. This is nothing but the we are obtaining the cached result here, right? So I hope this part is clear. Then what we will do, let's go with the valid divisors. Valid divisors, that is less than or equal to k. Let's go with the valid divisors less than or equal to k. Here in this case, it will be list of integer. So this I has to be capital. So right, so this is not small I, right? So list divisors which is of the type list. So this is fine. Let's go with the get divisors of n comma k. This is nothing but the valid divisors which is less than or equal to k, right? So let me do one thing. Let's move on with the next line here. If we don't have valid most, then we have to return -1. Nothing but if divisors is empty, if we don't have the valid most, or if the divisors is empty, then we have to return -1, right? So let's write the simple if condition here. If divisors dot is empty, then what we will do, will return -1, right? So if no valid moves, then we have to return -1 in that case. So let's go with a pure binary search, right? So let's go with a pure binary search now. Let's perform the binary search, right? So let's do one thing. I'll just initialize low to 1 and height to 60 here, and finally a result initially let it be -1. So we are performing binary search on the maximum steps. So let's write the simple while loop here as usual. If low less than or equal to high, then what we'll do within the while loop, so we have to calculate mid. if you know the binary search. So this will be low plus high by 2. We are performing the binary search on the index right here. So this one is fine. Low plus high by 2, or let's do one thing. Let's make use of the right shift operator 1. We can write the same thing like this as well, right? In this way as well. Low plus high by 2. So instead, we are going with the right shift operator. So this is fine. If let's make use of the can reduce to here, in this case function can reduce to function. We are reducing, right? So we are reducing the steps of a and b to 1, right? So here within the binary search, let's make use of the can reduce to 1. Can reduce to 1. So we have to reduce to 1, right? So we have to reduce to 1 here in this case. Let's do one thing. Let's make use of the can reduce to 1 function here. So without I mean before proceeding to this one, right? Before proceeding to this one. So let me do one thing here. Before, just give me a second here. Mm, so yeah, let's do one thing. I'll just come here. So let's go with the can reduce to 1. So here I'll just go with the static boolean can reduce to 1. This one, let's pass the parameters here int n comma list of integer. So this one, this will be divisors int, this will be max steps. This is fine. So within this function or the method, first step is let's go with the hash set here. So this will be set of integer. Let's do one thing. Let's make use of the current variable and let's initialize this one to the new hash set. So let's do one thing. Let's go with hash set. This is fine. Yep. We are making use of the hash set here and we need to start from n. So hash set provides the property called add. So I'll just go with current.add of n. So this is fine. The next step is let's go with the simple for loop here. So for int, let's make use of the step variable here. This will be step less than max steps here, and let me increment the step. I hope this part is clear. So within this for loop, what we'll do, let's go with a set again here, right? So this will be integer, set of integers. So this is fine. Let me make use of the variable next. This will be new hash set, new hash set. This is fine. So let's make use of the simple for loop again for int value. So this one will be current. And also within this for loop, let's make use of one more for loop. This will be for let's consider the individual divisor, right? So divisor, or let me consider d here. So this makes sense. I'll just go with d of divisors. So within the for loop, what shall we do? We have to try dividing. Means I'll just go with the value modulo d. If it is equal to 0, then next dot add of val by d. So this one I didn't show in the approach. So complete operation we didn't show in the approach. Basically the third step was basically to reduce the step of a to 1 and reduce the steps of b to 1. So that's what so this is the basically this is the steps to reduce a and b to 1, right? So we will be making use of can reduce to 1 here within the binary search, and we will be making use of that binary search within here, within the main function or the solve function, right? So don't get confused here. So this one will be val by d, right? So we are just trying dividing, right? We are going with the dividing. Basically we are trying by dividing here. So this is fine. So next what we'll do, if it is success, then we have to return true, right? If we can reduce to 1. If it is success, then we have to return true. If it is not success or if it is no progress, then we have to break out of that one. Then we have to break out of the loop, right? So here, if it is success, then we can write in this way. Next is the variable we have considered. So we can just go with the contains 1. Means if we have reduced that one to 1, then we have to return true in this case. If no progress, and if it is not this one, what do we call, if it cannot be reduced to 1, then we have to break out of loop, right? So here I can just go with if next dot is empty here in this case. So then what we need to do, we need to break out from the loop, right? So this is fine, I guess. So next thing is we need to current, we need to assign the current to next, right? So we need to check with the next value, right? So else, if it is not possible at all, then we have to return the boolean value false, right? We have to return the boolean value false. I hope this part is completely clear, right? So let's do one thing. We have to make use of this one. What do we call? Um can reduce to 1 to within the this one, what do we call, minimum steps binary search function. So here, before doing that, so just give me a second here. Mm, so yeah, let's do one thing. We have to get the divisors, right, get the divisors by making use of the parameters n and k. We have to get the divisors by making use of the parameters n and k, and also we have to go, we have to calculate the gcd as well. These two we haven't done yet. So first let's do one thing. Let's write the, let's do one thing, let's make use of the can reduce to 1, and then let's write the functions for the get divisors as well as for the calculation of the gcd. Or we can do one thing, let's do one thing, let's write the this one first, get divisor as well as the gcd function first, right? So then let's go with the this one, these two functions that we left in the middle. What are the functions? Min steps, binary search, as well as the solve, nothing but the main function. So before that one, let's make use of the get divisors, this one function. So I'll just go with static. So this one will be stuff integer. This is fine. So let me go with the function get divisors. So get divisors of int n comma int k. So this is fine. So within this list integer, so this one will be result equals. So let me go with new array list. So new of array list. So this is fine. Next thing is, let's go with a simple for loop here. Int I equals to I less than or equal to k, and so let me go with ampersand here. I into I less than or equal to n, and let's go with I plus plus. So this part, I hope this is clear, right? So this is just the iteration part. So here we have to get the divisor. So let me write the simple if condition here. If I modulo, sorry, this has to be n modulo I, right? N is nothing but the integer. So here this will be n modulo I. So here this will be, if it is equals to 0, what did I do here? N modulo I here, if it is equal to 0, then it is a valid divisor, and then we have to add that one, right? So here I'll be making use of the add property, that the add property. So here this will be I. This is fine. So next, we have to include the symmetric as well, right? So let's include the symmetric here. So this one, I really don't understand why we need to include the symmetric, but here this part, I don't know, but still, I tried avoiding this one, but it miserably fails basically if I ignore this part. So let's do one thing. Let's add this one, I not equal to n by I So tuple ampersand n by I, so less than or equal to k here, then result dot add of n by I. So I hope this part is clear, right? So we are just including the symmetric here. So let me come out of this one entirely. If whole n itself might be usable sometimes, right? So for that one, let's make use of the simple if condition here. If n less than or equal to k, then if whole n is usable, then we have to add that entire n. So we'll be making use of the add property for that. So add of n, right? So finally we have to return the result here in this case. So I hope this part is clear. So this is it for the get devices function. So let's move on with the next function, nothing but the GCD. So we have to calculate the GCD. So let's write the code for that. So I'll just go with static int here, static int. So this one will be, let me name this one GCD itself. So here let's go with int a comma int b. Euler's GCD calculation. So here I'll just go with while b not equal to 0, then so you would have used this one multiple times if you would have given the contests within the Codeforces or the code chef, right? So or even the LeetCode. So this will be a modulo b. So let me type this one quickly. This is just for the calculation of the GCD. So this will be a equals b, b equals t. So let's return a here in this case. So let's return a. So I hope this part is completely clear. I hope this part is completely clear. Let me come out of this one entirely. So before making use of the this one, what do we call, can reduce to I within minimum steps binary search and minimum steps binary search within the main solve function. Let's do one thing. We are left with the input output part. Basically here you can clearly see, instead of the this one, what do we call, buffered reader, we are making use of the fast scanner this time, right? So this is not the logic part. Basically this is the input output part, nothing but the template I'm making use of. So I'll just copy paste this one, so you can just have take a look into it if you're if you want to make use of the same template, or if you're this one trying to say this. So let me do one thing. So here I'll just remove this bracket. So let me paste this one. This is nothing but the fast scanner, right? This is nothing but the input output operations basically. So I'll just you can just pause this video, and if you're using if you're making use of same template, you can just type the same thing, or you can just have a look into it basically, right? This is nothing but the fast scanner implementation, that is this one, that belongs to the input output, right? Not the logical part basically, right? So you can just have a look into it, this one, fast scanner implementation, right? So we are done without this one fast scanner implementation. Only thing that is left is we have to make use of can reduce to 1, this one function within the min binary search, and min binary search within the solve function. First let's make use of the can reduce to 1 function within the min steps binary search function, right? So I'll just go with the this one. uh, let's continue here. So I'll just paste this one, can reduce to 1 of the parameters. Here we have to pass as n divisors as well as mid, right? N divisors as well as mid. So within the if result has to be equal to mid, as we are performing this one binary search, pure binary search, high equals mid minus 1, if you know binary search, right? So else what we are doing within the else part, so we are just going with low equals mid plus 1. So I hope this part is clear. Low equals mid plus 1. Let me come out of this one entirely. So we have to save the result somewhere. We have to save the result somewhere. This will be memo dot put of, so key comma result, along with the, we are storing the result along with the particular key, right? So we are storing the memo, so we are going with the this one, what do we call, we are storing the result along with the particular key, right? So we are going with the caching or the memorization by making use of the this one by avoiding the recalculation of say same for the same n comma k by making use of the hash map basically, right? So here in this case, this is it. Next we have to return result. Have to return the result. So this is fine. We are done with the min steps binary search function. So let me copy the same thing and let's make use of the min steps binary function here, right? Here within the solve or the main function, right? Within the solve or the main function where we have stopped actually in equals this one. Calculate GCD, we have already calculated GCD here. This function we wrote actually, so we are making use of GCD function here. This is fine. Then we are left with a equals x minus g. This one by this one we are this is the step, nothing but we have to solve or we have to reduce a to 1 and b to 1. We have this one stop till here. Next is to reduce a to 1 we are going with the min steps binary function, and to reduce b to 1 we are going with minimum this one min steps binary search function. So let's write that one, let's articulate the same thing in the form of code. So int s1, nothing but we are reducing the a to 1 here, so this will be min steps binary search of a comma k, right? A comma k. If s1, if it is less than 0, then what we'll do, we will go with a return minus 1. Same thing if s2 equals, so let me go with min steps binary search of, let me pass b comma k here. So this is fine. If s2 is less than 0, same thing, then we have to return minus 1. So let me copy this one. I don't want to type this one again, man. So let me paste it over here. We are returning minus 1. The final step is we have to go with the total steps, right? If you remember the approach, we went finally we summed up S1 steps to reduce to A to 1 and steps to reduce B to 1, right? Steps to reduce A to 1 plus steps to reduce B to 1. So here in this case, steps to reduce A to 1, this one, S1. And step to reduce B to 1, nothing but S2. Here we have to sum up S1 and S2. Let's return S1 plus S2. So this is it for the code. So this is it for the actual code. So basically this is the main code, right? So this is the main code. So here we have to calculate GCD, so we wrote the helper function GCD, or we went with the helper function GCD, right? So we have to calculate the minimum number of steps that is required to reduce A to 1 and B to 1. For that one we went with the helper function min steps binary search. Within the minimum steps binary search, we have to see whether we can reduce that one to 1 or not. For that one we made use of the helper function can reduce to 1. So we have the tight constraints as well within the question. So we are going with a binary search, and so we are making use of the helper functions. So the code is little bit lengthier. We could have went with other this one as well. Other ways, there are other ways to solve this problem, but basically the constraints are tight, and your test case will not get passed. So binary search is the best this one for this particular problem. This problem is designed to be solved with binary search, basically, to be frank, right? So divisor traversal and this one binary search, this works absolutely fantastic for this particular problem. So this is it for the code. I hope whatever the code that we have written is completely clear. Let me do one thing. Let's add the this one signature starter template. So let me do one thing here. I'll just come here. Let me paste this signature starter template here. So this is fine. So let's check with the input whether the code works or not. Let's debug if it doesn't. So I'll just come here. Let me copy this one. We have to get the same output here. 2 minus 1 minus 1 triple 3 6 minus 1. So let me paste the input here. Let me run this one. So we have the this one, what do we call, yeah, if s2. So yeah, here did I forget to give the parenthesis? Where is this line number 45? So here, so if we are making use of here, this has to be int, right? Not the if. So, this is wrong. So this is fine. Let me run this one again. So I hope this works. Let's see what happened here. Cannot find the symbol. fs dot next int. mm, k equals fs dot fs we have given here. So we have given fs here, right? For the fast scanner, we have made use of the fast scanner here. Where is this one? Fast scanner. What's wrong here? Next int, we have given next int here. This is also fine. So let's check what is wrong here. So let's see what are the mistakes that I have done here. Line number 27, it says cannot find symbol next int. So yeah, this here, this I has to be capital. So where we have given next int here, just give me a second. Yeah, this one I has to be capital, and here for this one as well, and for this one as well. So in the line number 27, 28 and 29. So let me run this one now. I hope 27, yeah, line number 27, this is fine. Here cannot find the symbol long key of this one, log n. So what is wrong here? Basically in the line number 56, right? So here this one I have given logarithmic n, right? So what's wrong here? Mm, this one has to be, just give me a second here. Here, yeah, this has to be long, right? So here not log n. So this we are making use of the long here. So here in the line number 56, let me give here long n. So this is fine. So in the line number, what do we call this one here? What am I doing? Mm, int s2. Oh yeah, this one. If s1, we are going with the s2, right? This time, not this one, s1. So I have to give s2 here. We are reducing the s2, or we are reducing the b to 0 here, not again s1. We are not reducing a again, right? So if it is not possible to reduce, then we are returning -1. That we have checked for s1 already. We have to check for s2 here. So this one I did wrong. So this is fine. So let me run this one now. This works. No, max steps S has to be capital here. So I can say this one. The line number 81 cannot find the symbol step. So in the line number 81, where is 81? So this one has to be max steps, where I have made use of the max steps here. Yeah. So parameter max steps here. This has to be capital S. This is fine. Let me run this one again. So next is E empty. E has to be capital here again. Line number 89. So many typos. So let me go with the capital E here. Is empty operation we are making use of, right? We are checking whether that is empty or not. So yeah, now we are getting the output 2 -1 -1 triple three 6 -1. So here we need to get 2 -1 -1 triple three 6 -1. We are getting the correct output right now. So yeah, there were some typos basically. There were some typos. Basically the code is long, right? Code is a little bit lengthier. So while typing, I did some mistakes. So I had to correct that. Basically now the code works absolutely correct. So what is the thing here is the main thing is there are only three steps, man, within the main function. This actually solve here. To solve the problem, first we have to calculate the GCD, and we are going with the binary search, so this is the main thing. To perform the binary search, to avoid the recalculation of n and k again and again, for that one we are making use of the hash map. And within the binary search, to calculate or to check whether it can be reduced to 1 or not, a can be reduced to 1 or b can be reduced to 1 or not, we are making another this one helper function can reduce to 1, right? So to calculate this one, we are making use of can reduce to 1, and within this one we have to calculate GCD of x and y, so we are going with the helper function GCD as well, right? And to get the divisors, we are going with the get divisors helper function as well. So main thing here is we are going with a binary search, along with the hash map, right? So other things are, we are making use of other things, or we are making use of the helper functions because the constraints are tight, and we have to uh, go with as fast as possible, right? So we have to write the code that runs as fast as possible. So in this case, that is the reason we have made use of the binary search, and this one can reduce to one function along with the get devices and this one GCD is we have to calculate the GCD basically. That is the reason we have went with the this one. That is exception. That is why we went with the GCD helper function. So I hope this part is completely clear, man. We went with step by step, right? So the last part here, again I'm telling this, I didn't type because this was related to input output, not the logic, right? So here I have just copy pasted this one. This you can just pause the video and have a look into it, right? So this is just related to the input basically. Fast scanner, we are going with a fast input reader, right? So fast input reader, nothing but in this case we are going with a fast scanner. Usually we were going with a buffered reader. This time we are going with a fast scanner. And for the output writer, we went with a print writer, right? So PW, we have made use of the PW uh, many times in the code, right? So this one I'm speaking of. This is nothing but the fast input reader. Line number 23, 24 is nothing but the fast output writer. So I hope the coding part is completely clear. Let me do one thing. Let me copy this one and let me paste it over here. And I hope this works, man, for all the test cases. Let's see. Let me hit the submit button. Let's wait for some time. You can clearly see here running on test one. So running on text 6. Let's wait for some time. Running on test 12, 13, 14. Yeah, let's wait for some time. And this has to work. Let's see. We have discussed everything step by step, right? So we have completely discussed the approach part and this one, what do you call, then the complexities part. Then we wrote the code. Exact same thing, whatever we discussed in the approach, we articulated in the form of code mainly, right? So this has to work. Let's see. So this is still running on test 33. So here you can clearly see the code got accepted. Means our code works absolutely correct in this case, right? So here, let me do one thing. Let's check the code once. Yeah, here. Yeah, everything works correctly, right? So again, I'm telling first, this is the main function solve. This is the main function. So we are going with the binary search. We went with the binary search, sorry. Here the first thing is accordingly with the approach, we have to calculate the GCD. We have to calculate the GCD, and then we have to perform the binary search on the indices. Basically, we are performing the binary search on the indices. So we are checking whether we are able to reduce the A to 1 and B to 1 or not by making use of the binary search, right? So to perform the binary search, to check whether it can be reduced to 1 or not, we are performing the binary search on the indices, not on whether it can be performed, I mean whether it can be reduced to 1 or not. Don't get confused here. We are just performing the binary search on the indices. Again, I'm telling, not for to check whether it can be reduced to 1 or not, we have written another function. We have written another helper function. Here you can clearly see this one I'm speaking of, can reduce to 1. So we are performing the binary search on the indices again to get the devices here, devices part. So we are going with the helper function get devices, and again I said the first main thing we have to do is we have to calculate the GCD. So we have written the GCD here. function for GCD here. So right, so I hope this part is completely clear. This is the logical part basically from here to here. What do we call? Yeah, from solve to here, and yeah, from static int solve to this one, static int GCD of parameter something, and all other things. These things are related to basically input output for this one, and we are making use of the fast input and fast output, right? So for the fast input, we are going with the fast scanner for this particular problem, and for the fast output writer, we are going with the print writer here, PW. For the fast scanner, for the fast input reading, we have written implemented the fast scanner here. So I can just have a look into it. You can just pause this one and look into it, right? So this is just the input output part. That is the reason I didn't type. So I just copy paste, I mean pasted this one. Yeah, right. So I hope this problem is completely clear. Very easy to understand. Only three steps, basically calculating the GCD, and we have to calculate the GCD of two numbers x and y. Then we have to check whether a can be reduced to a and b can be reduced to 1. After calculating the GCD, we have to calculate whether it can be reduced to a and b can be reduced to 1 or not. Then we have to sum up those steps required to reduce a to 1 and b to 1. We have to sum up those two, right? So these are the three steps. These are only the three steps, basically only three steps. Then we have to output the result that is resulted that belongs to input output basically. So these are the only three steps for the logic part. Again, I'm telling. So first we need to calculate the GCD. Then after calculating the GCD, we have to check whether the a can be steps of we have to go with steps to reduce the a to 1, and we have to go with steps to reduce b to 1. Then we have to sum up, finally the third one is, then we have to sum up step, if it can be possible. If it is not possible, then we have to return -1. If it is possible, then at that point of time we have to sum up steps to reduce a to 1 and step to reduce b to 1. So these three steps, that's it, right? Actually only these three steps. So we have written lengthier code because constraints are tight. We are making use of the this one binary search, as well as certain helper functions here, and also GCD and get devices function as well, right? To calculate to get the devices, and we have to calculate the GCD as well, and other helper functions along with the binary search. So that is the reason a code is little bit lengthier. That's it, right? I hope the solution part is completely clear, along with the approach and the complexities. For now, this is it. Thanks for watching, guys.